I'd like to welcome everyone to the Oxford Bristol Set Theory seminar, and it's my pleasure to introduce today's speaker, Mirna Džamonja, who is affiliated with the Institute for History and Philosophy of Sciences and Techniques at CNRS, and also the University of the Panthéon-Sorbonne in Paris, and the Institute of Mathematics and the Czech Academy of Sciences in Prague. And she's going to be speaking today on the topic of wide Aronszajn trees. So please go ahead, Mirna.
Thank you very much, Joel. It's very nice to see you, everybody. Of course, I was a member of the UK logic community for 22 years, and I have no intention to stop being one. But I did change my my position from the one that I used to have at the University of East Anglia to the ones that Joel has just quoted. Joel asked me to talk about this work. I have given a couple of lectures of this around the net, so perhaps some of you have seen some of them, but I certainly hope that, well, there will be some elements that will be interesting to you, even if you have seen the talk before. So let me just start this sharing, and then well, do you see? I think I should perhaps open this a little bit different. It looks good. Okay. So, well, actually, I think maybe I better open this with the Adobe Acrobat, because this is a kind of strange to move it like that. Sorry, let me just quit this and open it different. Yes, I think that looks a little bit better. So this work is joined with Aronszajn, who is at the Hebrew University of Jerusalem, as probably everybody on the planet knows Aron. And this is work that we have done the last time that we actually saw each other physically, which was in 2019, while things were looking better for traveling than they are now. So this is a paper that I'm very pleased to say was accepted by the Journal of Symbolic Logic, and it will appear there soon. So let me tell you what we mean by the concepts in this title. What are wide Aronszajn trees, and why we would be interested in them. So they are like Aronszajn trees, but they have been in the lockdown and have been eating too much and have gained on the side. So they have levels that are not necessarily countable. So it's just a tree of size and height omega 1. And what makes such a tree interesting is that it doesn't have any uncountable branches. So why people look at such trees? Their class will be denoted by T. So why is T interesting? Well, first of all, one particular instance of a tree like this is the classical Aronszajn tree, which has the properties that are given above, but in addition has countable levels. And of course, Aronszajn trees are of great interest. We will be talking about them as well. So let us also denote their class by something. I chose the letter A. So we have that the class A is a subclass of the class T. So we are going to look how these trees correspond to each other in a particular way, which will be this relation of weak embedding. But perhaps before I introduce this relation of weak embedding, let us just go quickly to some ways that we could use to build wide Aronszajn trees. Of course, building an Aronszajn tree is not a completely trivial matter, and it was first done in the 30s by Aronszajn, and the proof appeared in Kurepa's thesis. But since this has been almost 100 years, everybody knows how to build an Aronszajn tree, and probably everybody agrees that there is some work in it, however you take it, either with rational sequences or with coherent sequences. Well, to build a wide Aronszajn tree, you have to do no work at all. What you could simply do as an example of a wide Aronszajn tree is you take the limit ordinals less than omega-1, and let us call them alpha, and to each you associate an increasing omega sequence converging to that alpha. And then you just take all initial segments of these sequences and you get a tree which doesn't have an uncountable branch because the order type of each of these C alpha is just omega. So that's the easiest way to find an example. Of course, such a tree in general will have fat levels, so it will not be Aronszajn. So now let me say why we would be considering them at all. What is interesting about them? Well, you will see later in a slide that I have prepared that they are connected to some questions in model theory, abstract model theory. And this is how I came to know about them, which I will tell you about as well. But one particular thing about them that we will be looking at in this talk is the possibility of having one which in some way embeds all of them. So how could you embed one tree in another? Of course, you could just try to look at order preserving injections. But people who study these questions for various reasons are not particularly interested in injections. They are more interested in this relation of weak embedding, which now I will define. So we say that the 3t is weakly embeddable into the 3t prime if we can find a function f from t to t prime which preserves the strict order. So you see in such an embedding, there is no requirement that the embedding is injective. Two points that are incompatible to each other could well go to the same image. But such a function is injective on branches. So such an embedding preserves branches of the tree. So somehow you can think of this notion as saying that the branch structure of T prime is at least as complicated as the branch structure of T. And as I mentioned, studying such trees is motivated by the fact that they are used as clocks in Ehrenfeucht games that compare models of size Aleph1. So maybe let me just make some pictures about it. Let's see, I prepared something. So I'm going to stop sharing this screen and I'm going to start sharing my iPad to show you a picture. So we have that. So let us see what I mean by Ehrenfeucht games. This is an interesting topic in its own, so that's why I want to make this picture. So you know this very nice theorem independently obtained by Ehrenfeucht and Fraïssé in the 40s, I think 50s, I don't know. If you have two countable models M and N, and you want to decide if they are isomorphic to each other, what you can do is to play a game. And in this game, you will have a spoiler and a duplicator. And so the spoiler will try to demonstrate that they are not isomorphic by picking points in one of the two models and saying, well, the duplicator cannot find a point that corresponds to this one, but the duplicator will be able to find an isomorphic image, so the point that has the same properties locally as the point that the spoiler has chosen. And the theorem of Ehrenfeucht and Fraïssé says that in the case of countable models, if the duplicator can survive at any finite time, so can continue this game as long as he wants for an infinite number of steps, then these two models are actually isomorphic. So the spinning strategy of the duplicator gives us an isomorphism. And of course, one could immediately ask if this is also the case for models of size Aleph1. And this actually opens the Pandora box. This is not at all true. I mean, the analog of the Ehrenfeucht theorem is totally not true. And much study has been done about this question, especially in the Finnish school of model theory. And one thing that people have studied in this context is how they could make the life of the spoiler a little bit harder, so that there would be an analog of the Ehrenfeucht theorem if the duplicator has a winning strategy in that game that is easier for him than the original game. So to make the life of the duplicator harder, one could associate a clock. And one idea of what kind of clock we could associate is to take a tree like these trees that we have just discussed from the class T. And we ask the spoiler at the beginning to have to choose a point in this tree. And then the game has to go down. So of course, we know that since the tree has, this is a tree, this is well founded, the predecessor of these points are well founded, this tree is actually, so is going to finish in a finite time. And well, I will not tell you the whole story of this. Perhaps I'll stop now telling you about this game, but this is how the trees that I have been telling you about actually came to be. That was the main motivation of studying them. Another motivation of studying them came through, again, through the Finnish school, through a topic that has since become known as generalized descriptive set theory. But in this paper, in a paper of Mekler and Väänanen in 1994, they actually already started that subject by looking at how such trees in the class T could lead to some analog of descriptive set theory for the uncountable. So there are some theorems in generalized descriptive set theory that one can find in this paper. That has been another motivation for studying such trees. Okay, so let's go back.
Can I ask a question about that?
Yes.
So what's the difference? Because if you're running the clock down in the tree, then it seems that the only thing that matters about a node in the tree is what ordinal level it's on. It's just counting down in the ordinals. So you're not really, if you're counting down in the tree, it seems that you're just using, it's the same as picking the ordinal level and then going down to the earlier level.
Yes, indeed, you are right. But they do study versions that are more complicated. In the version that I've just explained, you are right. You don't need a tree, you just need an ordinal.
It seems, do they ever go count up in the tree? Because that would seem to be
that
interesting,
would,
because
that
then it would peter out at some
correspond.
countable.
Yes, that's right. That's that. In that way, you would stop because you don't have an uncountable branch.
I see.
Yes,
Okay. Thank you.
Thank you for the good comment. Okay, so let's go back then to those slides. Where are they now?
Can I ask a question related to that? Like, the idea was that you said if you make it harder for the spoiler, then you really know if the duplicator wins, it really won. Is that the idea? Like something like that for the?
Yes, so the idea would be to, by making this game harder for the spoiler, you would make the win of the duplicator strong, so that the duplicator would actually make an isomorphism. Is that all fine now? Yeah, great. Okay, so then I will talk, and I hope that we will no longer have the problem. And I want to be able to be drawing, but never mind. So anyway, I think that perhaps we can now move on to what we want to do. What's this? Okay, so this is the paper that I mentioned in 1994. So they had a very large project on this class T, motivated by various reasons, and they were interested in the universality question. So if you play these games like the Joel proposed, you play the games up the tree, Then if you have a tree that is that is the widest possible, it embeds everybody else, then the spoiler can go up all the time and doesn't and will be able to win against the duplicator. That's the intuition. So for example, imagine if you had a branch that goes omega 1 many steps, then having this tree doesn't stop anything from happening. So that's why we do not have the branches. Of course, a branch would trivially embed all these trees. So the more interesting question is there an element of T which is maximal in this weak embedding relation? And now probably most of you know this very nice very nice result of Kurepa, who invented the sigma functor. The sigma functor is a way to make out of one tree another tree, and this new tree never embeds into the original one. And how do you do that? Well, you simply take your original tree, and then you associate to it the tree of all the increasing sequences in this tree, in the tree that you started from, and you order it by initial segments. And a little bit of thought shows you that this tree does not embed weakly into the new tree. The problem that you might have is that the cardinality of such a newly obtained tree is too large. But in this class A or T, if you assume the continuum hypothesis, the tree of initial segments will still be, of increasing sequences will still be of the same cardinality as the original tree. And this will show you that there cannot be a universal element in this class. So really the question of Mekler and Väänanen is only interesting if we do not have CH. Now, this is happening in 1994, and of course, people are still looking a lot into what's known under MA. And so the very natural thing to ask is what happens under MA? And so this is the tree. What happens under MA? Well, let us try to solve this problem. You take an Aronszajn tree and you want to show that it embeds into another tree, for example, using some CCC forcing. How would you do it? Well, it seems that there is an obvious way of doing that. You take a finite segment of your tree and you put an embedding. And actually, if you do this forcing, you can easily prove that it is CCC. And this is what they did. However, unfortunately, this argument is wrong. So they have taught in their paper that MA actually implies that there is a universal element because they have found the CCC forcing that I've just described. But this CCC forcing has one problem. It doesn't obey the density requirement. Now, since I'm too afraid of my own iPad, I'm not going to show you how the density fails, but there are some pictures on the slides that we will see later, which will show you where this density argument in their case goes wrong. So this mistake was realized quite quickly, maybe a year or two after the paper, by Todorcevich, and he started studying the class of trees where basically where such a mistake cannot happen. Those of you who know the definition of Lipschitz trees will perhaps recognize that in this class, such a density cannot happen. The Lipschitz trees have a rather technical definition, which I will not tell you now because I don't need it. But under MA, they happen to be exactly the class of coherent trees. So these are exactly the trees that you can obtain by taking a coherent sequence like those C alphas that we have mentioned before and making a tree out of it. And so Stevo has a very nice paper which I don't know why it took until 2007 to appear, about these Lipschitz trees. And he has, of course, the book about coherent sequences in which you can see coherent trees. So combining the results from this paper and the book, one can see that Todorcevich proved that under MA, the class of Aronszajn trees does not have a universal element. In fact, he proved that under MA, these Lipschitz trees are cofinal in the class A, and he also proved that there cannot be a universal Lipschitz tree. So that is about the Aronszajn trees. Now, what we prove is the following fact. Under MA, the class A is cofinal in the class T. So this implies that there cannot be a universal element in the class T, because if it were to exist, we could then, using this theorem, associate to it an Aronszajn tree into which we embed this wide Aronszajn tree that thinks that it is universal. And then this Aronszajn tree would be universal for all wide Aronszajn trees, in particular for Aronszajn trees, and that cannot happen. So that's a corollary of this theorem. So the class T doesn't have a universal element under MA. And we note that upon hearing these results, Todorcevich pointed out that his proofs could also be made differently to give the same result, but the proofs are that would give a different proof of this result. So our paper contains two main forcings, two main results, which are both obviously based on new CCC forcings because they are about MA, and what turns out to be important, appropriate families of Aleph-1 many dense sets. So the first result gives another proof of Todorcevich's result, which states that under MA, the class A doesn't have a universal element. So we do not pass through the class of Lipschitz or coherent trees. We do it differently, we do it directly. And I think that this result has some interest of its own, even though the proof of Todorcevich was already known. Our proof gives a new way to specialize Aronszajn trees, and perhaps it is interesting for that reason. And the second result is the theorem that I have just told you, which is the theorem that the class A is cofinal in the class T. So that theorem is proved by introducing a CCC forcing, which embeds a given wide Aronszajn tree into a usual Aronszajn tree. So let me then show you some of these proofs and what were the difficulties. So we will represent our A in what is usual by taking as representatives of the class A, the set of all normal rooted omega-1 trees, which have no uncountable branches. Normal just means that, well, there is a root. This is rooted. Normal means that if you have a point of limit height, then it determines the branch. So you cannot have 2 points on a limit height which have the branch which is below them, which is the same. Usually there are some other properties that one can throw into the definition of normal, but for us only these two are important. In fact, what we're going to do is we are going to index any level of these trees by a subset of the ordinals, countable ordinals, and the alpha level will be indexed by the ordinals in the block between omega alpha and omega alpha plus omega. And let me also introduce a shorthand. I call the height of a countable ordinal the unique block of this type to which this countable ordinal belongs. And the root, we will consider it to have level -1. So note that every Aronszajn tree embeds into one of these forms, so we can just work with such Aronszajn trees. And this is what I said of what we mean by being normal, just that if we have 2 points of the same limit level, then they must differ at some level before. And now there is some important notation for us. We will be working with the pairs of trees. So our forcing will actually specialize both trees at the same time. That will be the trick. There will be something called specializing triples. And these specializing triples will consist of 2 Aronszajn trees and 1 function C. And for those 3 trees, T1 and T2, we will be working on the level-wise Cartesian product. So we look at any level alpha, and we just look at the pairs x and y such that x comes from the alpha level of T1 and y comes from the alpha level of T2. And so for such pairs, we are going to denote by alpha of x and y their common level. And now I introduce this idea of specializing triples. So we have triples that consist of T1, T2, and C, where T1, T2 are Aronszajn trees. And C is a function from this level-wise product, but we only look at limit levels. So we take the union over all limit delta, level delta of T1 times level delta of T2. And we will have a function which to such pair from such a product associates a natural number. And what we will have is that if 2 pairs have been associated the same value on the C, then they cannot have the same height. 2 different pairs, they cannot have the same height. And moreover, both the first coordinates and the second coordinates are incompatible to each other. Well, I suppose this latest part implies that the heights are different, but I wanted to emphasize it. And the place where x1 and x2 differ in T1, this is this notation delta, which is common when one studies trees. This is the level, the first level where x1 is different than x2. So this level on T1 side is strictly larger than this level on the T2 side. Now you may wonder where this definition comes from. Why do you want such a thing? Well, in fact, while looking at Todorcevic's paper and the paper that Jouko Väänanen and I had some time ago, we actually proved some positive universality results. When we restrict our attention to embeddings that satisfy the opposite of this. So we were able to study embeddings between trees where the delta on the side T1 is less or equal than the delta on the T2 side. So really the difficult embeddings are the ones that satisfy this. That is where the motivation for this somewhat strange definition comes from. And now let me then, so I hope that you have taken this definition, it's important. Let me now make some observation. First, some simple observation. Every rooted normal Aronszajn tree is isomorphic to a tree in A. I think this is probably very easy to see for everybody, so I'm not going to spend time on it. This is an important one. If you have a specializing triple, then this specializing triple means that both T1 and T2 are special Aronszajn trees. So this function C, if you manage to find such a function C, you can prove that T1 and T2 most are both specialized by some close relative of C. Now, I had intended to show you this proof on the board, but I cannot. Let me also say the third property. If we have such a triple, then T1 is not weakly embeddable in T2. So this specializing triple idea kills two birds at the same time. It specializes the trees and also kills the idea of embedding T1 into T2. Yes. So let me perhaps just tell you in words how you would prove the second part of this. And then, you know, the paper is available on my website. You can look at it if you are interested. So the way to prove this is to first look at in T2 and choose a point. So for example, to prove that T1 is special, you're going to define a specializing function. So first you look at T2 and choose a point at every limit level. Call this Z delta for the limit level delta. So you have this set of Z deltas, and you can do this because the height is equal to omega 1. And then when you have something of limit level delta in T1, you want to define what your specializing function d of that point is. So let's suppose you have some x and you want to define what is d of x. So what you will be doing is to look at what C does to the pair x, comma Z delta, where delta is the level of this x. And you're going to make some small coding trick, and out of that will come out the specializing function. And well, for the third part of this lemma, you should make an observation that if there were to be an embedding between a 3T1 into a 3T2, then there is one which preserves levels, because you could just take the embedding and then cut it to the define. If this embedding is f, then just define g. G of x is f of x restricted to the height of x, and that's well defined. And then using such an embedding and this property of decreasing deltas, you get a contradiction. Now let me pass to this theorem. This theorem says that for every Aronszajn tree, there is a CCC forcing and a family of Aleph1 many dense sets in it, such that every generic filter for this family adds a tree and a function, such that this new tree, our given tree, and the function form a specializing triple. So this shows under MA of omega 1, this T cannot be universal for Aronszajn trees, because this forcing is going to add a tree which witnesses that T is not universal. So that's what I've just said. Now let me show you this forcing. So you have this T, and now what you're trying to do with the T star is to add this T star, which are, so T star is going to be the first coordinate of the specializing triple. And what we're trying to do is to look at a finite part of T and imitate it somehow to obtain this T star. So this finite part of T is called V of P. So we take some finite part, and we are building the T star by the finite pieces U. And well, U is going to contain the root and be finite, and the root is also in this V. And when I said imitate, this is what I meant. What I would like to do is to associate to every element of this VP something which is going to be in the C connection with that point. So if I have some alpha which is in this VP, Then in this UP, I'm going to find beta, which has the same height. Now, what do I mean by height? Well, this is where I'm going to use the fact that I am indexing everything by blocks of omegas in countable ordinals. So any countable ordinal has a height, and that will be the same height that it will have in this tree once we are done constructing it. So this makes perfect sense. Then this here is a partial order, which is going to become the tree order on T star. And this order, of course, is going to respect the order on the ordinals. And what we will want to do is that in this condition UP, we're going to decide exactly for any two nodes where they're going to, this is an intersection, or where they're going to stop differing. This is their delta, if you wish. Because imagine these alpha and beta as being members of the tree. And we have this order, so this intersection means the largest element which is below alpha and beta. So we are going to fix that in one condition, and it's never going to change by bigger conditions. And C, of course, you can guess this is going to be a function that is going to build a specializing triple. So it's going to be defined on these products over the limit levels. It's going to go to omega. And it's going to satisfy exactly what we need in order to become a specializing triple. So if we happen to associate by C the same value to two different pairs, then these two pairs do not have the same height. And we have this requirement on the height of x1 intersected with x2 being larger than the height of y1 intersected with y2. This height is going to become the level of the tree. So, and well, I write my forcing this way. P is a weaker condition than Q. So the order is given by inclusion. We give more information, we get a bigger condition. And everything has to fit, of course. What we have decided about the order has to continue. What we have decided about the function has to continue. And as I have said before, the intersection and the root information is going to be preserved. So that's the forcing, easy. Now, first, why is this forcing CCC? If you were to write down the forcing and play a little bit with it, you would come to the point where you need to use this lemma that was proven by Baumgartner, Malletz, and Reinhardt in their celebrated proof that under MA, all Aronszajn trees are special. But in fact, if you know this proof, you will know that you do not really need to work with Aronszajn trees. It applies to any tree of height and cardinality aleph 1, if it doesn't have any uncountable branches. So what it says that if you have a tree, which is actually a wide Aronszajn tree, it has height and cardinality omega 1, it has no uncountable branches. And now you take an uncountable collection of finite pairwise disjoint subsets. So like, for example, the conditions that you have cleaned up in your delta system lemma in this forcing. What it says that, excuse me, you can find two out of those finite sets that every element, such that every element in the first set is incomparable with any element in the second set. And this is something that's very important in their proof, and it's also very important in our proof. Well, if you look at Yek book, the lemma would be stated for Aronszajn trees, but this is not how it is stated in the paper. And it is not what we need. Okay, so that's basically what is done here. And as I said, the point here is the density. So the proof that Mekler and Väänanen had failed because they have neglected to consider density. How do you add a new point? And there is some work to be done in this forcing as well to obtain this density. But since this point comes even more clearly in the second result, I'm going to pass to the second result and then show you what can go wrong with the density. So the second result, remember, is that for every tree in the class of wide Aronszajn trees, there is a CCC forcing and a family of dense sets in it, such that the generic filter adds an Aronszajn tree that weakly embeds the tree we started from. So this in particular means that under the assumption of MA of omega 1, the class A is cofinal in the class T. For this theorem, we do not need to use we are not going to use the idea of specializing triples. I showed you that idea because I think that, well, there are still many open questions about Aronszajn trees, and perhaps these new ways of specializing trees can be of some help. Let me mention one problem which has been open since the 1970s, since 1975, and which fortunately has seen more than one wrong solution to it, including one to which I contributed. This is the question: if the combinatorial principle club implies that there exists a Suslin tree. And that's a hard question. And perhaps a new idea of specializing trees might be helpful in solving this question. I don't know. But I mentioned it here because there are some younger members of the audience who perhaps do not know this question. So let me go on to show this theorem now. We're going to no longer talk about specializing trees. So how are we going to do this forcing? So let us just recall we have a given T and we want to force another tree, which is Aronszajn, and such that T embeds into it. So we are sort of going to do a mirror image of what we have done. So far, we are now going to take this tree. We can as well assume that it is a subset of the set of countable sequences of countable ordinals ordered by inclusion, because every wide Aronszajn tree is a isomorphic to a subtree of this. So we are given such a tree, and now we're going to force this Aronszajn tree. And so UP are going to be finite pieces of T, and VP are going to be finite pieces of our new tree, which will be ordered by this. And this will be the embedding. And C is going to be something else than the specializing triple. We will see. So this is what I've just said. U is a finite subset of T. VP is a subset of omega 1, because our new tree will be indexed by the ordinals in omega 1. And this is an important requirement which gives us some headache when we prove CCC. UP is closed under intersections. This is a partial order on VP. FP is a surjective weak embedding from UP to VP. We have that the height of every FP of eta is equal to the height or length of eta for any eta in T. So in other words, F is a level preserving weak embedding. And here is a function C. So the function C is also a function from V into omega. And it has the property that it's a little bit like a specializing function. That is, if alpha is less than beta, then Cp of alpha cannot be equal to Cp of beta. Of course, if alpha is less than this new order, then beta in this new order less than P. And the order is given by inclusion, as you may imagine. So let me show you finally this density. I've been mentioning density a lot in the talk. So what I need to prove is, of course, that this in this way I am able to cover the entire 3T. So I have to produce a family of dense subsets such that the domain of the union of their FPs is the entire T. And the dense sets, of course, are not surprisingly just simply the conditions that have a given node of the tree inside. And now let me show you the main point. What can go wrong when you do this forcing? So far, everything is easy. So imagine that you are in a situation that you need to add this row, and you have committed yourself to something like this. You have committed yourself to a node sigma here, and to a node sigma prime, which have the same height, to the node tau, and to the node tau prime, which also have the same height. And sigma and tau actually intersect in this row. And now you have also committed yourself, let us say row has level alpha. And you have committed yourself to what happens to the restriction of tau prime to alpha, which is here called, excuse me, rho prime. And you have committed yourself to what happens to the restriction of sigma prime to that height, which here is called rho double prime. And you see, if the picture really looks like this, let us say what is in black is what's inside of your given condition, and now you have to add this row, then you might find yourself in the situation that this rho prime and this rho double prime have been mapped to different values in your image. So f of this is different than f of this. And that's really bad news, because and f of tau prime is the same f as f of tau, and f of sigma is the same as f of sigma prime. There is nothing to prevent this situation. And then if this happens, then you are really in trouble, because this row has to be both below sigma and is below sigma and tau. So f of this has to be both below f of tau prime and tau, and f of sigma prime and sigma, and it has to have this height. But if you have committed that this and that have different values, then you are stuck. And this is actually how the problem arose in the work of Mekler and Väänanen. Something similar to this is what led to the mistake in their paper. And to prevent this, we require our condition U to be closed under intersections. So we do not run into this trouble, because this row would have already been in our condition if sigma and tau were inside of that condition. So that lets you fly by the density requirement, but of course that makes the proof of the CCC of this forcing harder, because when you glue together the conditions that you get from cleaning by the delta system lemma, you have to close them under the intersection. And well, the point is that we can do it because of the way that we define this C. So the C function actually lets us doing that. Well, so now I would like to say a few more words about what else could be done with this. What are the questions to investigate at this point? Of course, the obvious thing to ask is what happens at Aleph 2? Now, at Aleph 2, we know that there are situations when there are no Aronszajn trees or analogs of Aronszajn trees at Aleph 2. But it is very easy to build wide Aronszajn trees, wide Aleph 2 Aronszajn trees, exactly by the same trick that I have mentioned, by taking a sequence, just a sequence of club sets in limit ordinals. So such trees exist also just in ZFC on Aleph 2, and we might ask the same question. This is getting hot because MA of omega 2 is also a reasonable axiom, and we know how to, one of the rare axioms that we have for dealing with objects of size Aleph 2. So it looks like we could just do exactly the same thing that we have done here. But no, in fact, that's not true. If you remember, one of the main points of this argument was the CCC argument, which uses the Baumgartner-Mallet-Reinhardt lemma. And that lemma uses in a very crucial way the fact that the tree does not have an uncountable branch. And it cannot work the same way for trees which do not have the branch of size Aleph 2, because we are still trying to prove that some forcing is CCC if we want to apply MA of omega 2. So if we want to do this problem on omega 2, the things are not so straightforward. And what I have been looking at recently, and hope to be able to say something about, is to solve the problem on Aleph 2 using not MA, but using the Niemann way of forcing objects on Aleph 2 by finite conditions. But then rather than CCC, we have these two sides, two kinds of side conditions, two kinds of models as side conditions. So I hope to be able to tell you more about that at some point if it works out, but that's what's cooking. Thank you very much for your attention, and sorry for all those problems that we had with my presentation.
Well, let's all thank the speaker, Mirna, and we can open things up for questions. Are there any questions? Just unmute and go ahead.
I had a question. Earlier we were talking about that game, and I just like to clarify that when something has a universal element, does that make it more difficult for the spoiler or less difficult?
So this tree is going to actually help the spoiler win, because if he is given such a tree, this tree is for all practical purposes like a branch of height omega 2, of length omega 2. So actually this tree, because it has such a wide branch structure, is going to help the spoiler. Okay. This is the intuition, of course, because such a tree hasn't yet been found out. And let me tell you, Erin, I've actually, your question is very, very interesting in its own, but it also reminds me that I didn't tell you what the main open question about this whole thing is. Okay. We do not know if there is any model in which there is a universal wide Aronszajn tree or Aronszajn tree. So it's perhaps just the ZFC result that there is never such a thing.
Okay, it's possible that there is no
That's right.
Ever a universal element. Okay.
Yes.
So I have a question. It's maybe related to Aaron's question, and that is how should we think about the significance of the existence of a universal tree? I mean, of course, I understand what it means for there to be one, but what is the significance of the existence of such a tree, or what's the right way for us to think about why?
Well, apart from those, of those games, one could also think of the generalized descriptive set theory, because in descriptive set theory also, well, you know, the branches of a tree correspond to closed sets, and this is the same thing also in generalized descriptive set theory. So somehow these embeddings give you embeddings between closed sets.
I see.
Yeah, so.
Okay, all right. Are there any other questions? All right. In that case, let's all thank Mirna again for a wonderful talk. Really quite interesting. So thank you so much.
Thank you very much. Thank you, Joel, for inviting me. Thank you, Joel and Philip, for inviting me. Okay, thank you. Thank you.
And also, let me just mention that in 2 weeks, I guess it's 2 weeks, right? Yes, we have Gabe Goldberg will be speaking for us on even ordinals and the Kuhn inconsistency. So everyone please come back in 2 weeks.